Today, India operates the Launch Vehicle Mark III, a heavy-lift rocket with a flawless 100% mission rate over 9 consecutive deployments, and is fully capable of lifting massive payloads into orbit. But unlike the space agencies of the United States or the Soviet Union, India's program did not emerge from a geopolitical race for orbital supremacy. It was created to solve immediate terrestrial problems for a developing nation, managing agricultural yields and predicting monsoon weather patterns. In 1962, Dr. Vikram Sarabhai established the Indian National Committee for Space Research. His guiding philosophy was strictly practical. He argued that technology should act as a direct tool for the benefit of the common man, prioritizing earthbound utility over cosmic prestige. This mandate led to the creation of Aryabhata in 1975. Weighing 360 kilograms, India's first satellite was built from the ground up to track weather systems and monitor natural resources. Aryabhata worked perfectly in orbit, but getting it there revealed a severe vulnerability. India had to rely on a Soviet Cosmos 3M rocket for the launch. Depending entirely on foreign launch vehicles meant other nations controlled India's access to its own orbital infrastructure. Achieving total autonomy became a strict requirement. The first attempt to launch a satellite domestically was the Satellite Launch Vehicle, or SLV-3, in 1979. The rocket failed to place its Rohini technology payload into orbit. However, ISRO engineers treated the flight as a massive data-gathering exercise, recovering critical telemetry on the vehicle's structural responses. They applied that failure data immediately. The very next year, in 1980, the modified SLV-3 successfully injected the RS-1 satellite into low Earth orbit. This graphic illustration shows the extensive fleet of INSAT and GSAT series satellites that followed. With domestic launch capabilities secured, ISRO rapidly deployed these remote sensing and telecommunications networks, establishing the backbone of modern Indian agriculture and broadcasting. As the utility of these satellites expanded, so did their mass. India's spacecraft were becoming too heavy for early rockets to lift, creating an urgent bottleneck. They needed vehicles capable of carrying thousands of kilograms. Iterative testing led to the Polar Satellite Launch Vehicle, or PSLV, a highly reliable workhorse rocket with liquid stages that executed dozens of successful flights. Yet the PSLV had a strict physical limit. It lacked the thrust required to push heavier communication payloads out to a geostationary orbit 36,000 kilometers away. To cross that threshold, ISRO needed highly complex cryogenic engines. In the early 1990s, India attempted to acquire this technology through an agreement with the Russian space agency, Glavkosmos. The United States intervened and blocked the transfer of the cryogenic technology and design schematics. Locked out of the global market, ISRO committed to a punishing 2-decade timeline to reverse engineer and develop liquid-fueled cryogenic engine technology entirely in-house. By forcing India to build its own testing facilities and propulsion modules, the embargo catalyzed absolute self-reliance. This effort directly yielded the Geosynchronous Satellite Launch Vehicle, ensuring India would never again be denied access to space. Mastering the PSLV and the homegrown GSLV provided the exact thrust profiles required to send hardware beyond Earth orbit. This annotated map of the Moon highlights the specific geographical targets of Chandrayaan-1. Deployed by a PSLV in 2008, this mission secured the historic detection of lunar water. Curious, appreciative. This board features the first frames captured by the Mars Orbiter mission, reaching orbit on its first attempt in 2014. Not precision was earned through paranoid backup testing, autonomous software, and systems redundancy. Lessons salvaged from early SLV crashes. When the Chandrayaan-2 lander crashed into the lunar surface in 2019, ISRO maintained total transparency. They spent the next 4 years analyzing the orbiter telemetry, writing new guidance software, and reinforcing the landing legs. Those specific hardware and software corrections allowed Chandrayaan-3 to execute a flawless soft landing near the lunar South Pole. ISRO's interplanetary achievements are the compound interest of 40 years of analyzing failure, making strict corrections, and flying again. Today, ISRO is transferring its commercial rockets, like the small satellite launch vehicle, to private Indian companies. This frees the agency to focus on deep space scientific research, including the Aditya L1 Solar Observatory and upcoming space docking experiments. The path from monitoring crops on Earth to operating heavy launchers in deep space required strict adherence to practical problem-solving. A developing nation built a permanent presence in the cosmos by addressing the brutal realities of engineering and resource management on the ground. The journey to the lunar South Pole didn't start in a multi-billion-dollar complex. It started with a handful of scientists, a few bicycles, and an empty church in a coastal village.